Let's solve another thermodynamic problem that involves using the property of entropy. This time, let's take a closer look at a Carnot cycle. The TS diagram below shows a Carnot refrigeration cycle for which the substance is refrigerant 134A. Determine the coefficient of performance. So let's look at the way we have modeled refrigeration and power cycles in the past. We have a refrigeration cycle located between two thermal reservoirs, a cold reservoir and a hot reservoir. Work is put into the refrigeration cycle, and temperature, the cold reservoir, then transfers energy via heat transfer into the refrigeration cycle. And then energy is transferred from the cycle to the hot reservoir via heat transfer, QH. So this is what this refrigeration cycle looks like. So we have this refrigeration cycle between our reservoirs. And here's a TS diagram. Now this is a Carnot refrigeration cycle. Carnot indicates that this is a reversible process. And refrigeration cycles go counterclockwise on a TS diagram. If it were a Carnot power cycle, it would progress clockwise. So we can see that there are four processes forming this cycle. Process 2-3 is it's an adiabatic compression, and this is where work is added. Work is required to compress the refrigerant. And then there is a constant temperature heat transfer process. This is heat transfer at constant temperature, and this would be the hot temperature, TH. Then there's an adiabatic expansion from state 4 to state 1. And then another constant temperature heat transfer process takes place in process 1 to 2. So we need to find the coefficient of performance for this refrigeration cycle. Well, how do we find the coefficient of performance? For a refrigeration cycle, we give the coefficient of performance the term beta. And it's just what we want divided by what it costs us to get it. But what we want to do is keep the cold side cold. So we're interested in the heat transfer QC. And what we have to put into the cycle to cause this heat transfer to take place is the work. So beta is just QC over W. Now, an energy balance of this cycle yields that the work is just QH minus QC. So let's substitute QC for work, and we'll get beta is now QC over QH minus QC. Now, we know for a reversible process only, QC over QH is TC over TH. And so we can substitute in this Carnot cycle that beta for this reversible cycle is TC over TH minus TC. Now we already know TC, that was given, that's at state 2, and that is at 0 degrees C, and we need to work with absolute degrees, so that is equivalent to 273 degrees Kelvin. Now at state 2, we can go to the 134A saturation table at 0 degrees centigrade. And we see that S2 is just the value of S sub G in the table. It's a saturated vapor. And we get an entropy value at this state of 0.9190 kilojoules per kilogram K. Now in state 3, we'll note that S3 is equal to S2 because that's a constant entropy process. And so now state 3 is defined as R134A. It's superheated, and it has a pressure of 16 bar. And the other independent property we know is that its specific entropy is 0.9190 kilojoules per kilogram K. So in the superheat table, we can look at the subtable, which is at 16 bar. And we're looking for this value of 0.9190. Well, we don't quite find it, but we see that it's between these two rows. So it takes place somewhere between 60 and 70 degrees. we'll interpolate here to calculate the temperature. So I like to do my interpolation factor independently, and that is just going to be the value of entropy at state 3, which we have, minus the value of entropy at 60 degrees over the entropy at 70 degrees minus the entropy at 60 degrees. We have those values from the table and calculate that the interpolation factor is 0.3119. Now I can calculate T3. It's just 60 degrees plus the interpolation factor F times the difference in temperature between the two rows, that's 70 minus 60. And I calculate that T3 is 63.12 degrees centigrade. Now we need this in degrees Kelvin, of course. And because T3 occurs at our high temperature, we know that TH is T3, and that is 336.12 degrees Kelvin. So now I can calculate beta. It's 273 over 336 minus 273. Get a value for beta of 4.33.